So let's continue with other example where n is equal to 10, p is equal to 0.14, so entropy is 0.58, and you multiply with the 10, that is 5.8, and the size of the typical set is 111, and then this is an approximation with the AEP. So the probability of occurrence of each sequence is 1 over 111. So that is 0.009. So each one occurs with equal probability, which is 0.009 under the assumption of AEP. And then there are total of this many sequences because n is equal to 10. Okay, and we can compare this, typical set probability, AEP probability with exact calculation. A sequence with no one is this, sequence with a single one is this, sequence with 2 ones is this, sequence with 3 ones is this, and so on. And then if we add them up from starting from the first and go on down the line, then up to when we get up to this many, it is almost 96%. Okay, all right, so obviously this one has large departure from this probability, right? So when we compare each one of them, like the probability of occurrence of each one is 0.036, this one is 0.22, and 0.0059, this one is it's even smaller. So obviously, it is somewhere closer to this one, but not, quite very close, right? But you can say that it is close to this number, for example, of this one, especially when it is n times p is, in this case, is 1.4. So this one is supposed to be most typical, or 2 ones, right? So this one or that probability is the most typical probability. So so that's the argument of AEP using n is equal to 10, and we can move further with n is equal to 100. Then the p is equal to 0.02. So entropy in this case is this, and h is about 14. The size of the typical set should be 2 to the power of 14, which is this, 18,000. And the probability is 1 over 18,000, which is on the order of -5. 10 to the -5, right? So, and comparing with this one is like 10 to the third, and so it's 10 to the 30th power. So obviously the typical set size is very small, and if we do exact calculation again, so most probably is this one with no one at all, and single one is this one. So each occurs with this probability, and then you multiply with 100. So that's the probability of sequence having single one. and so on and so on. Obviously, in this case, this one is most close to this number right here. And that is the case with the 2 ones, because that is exactly the case with n times p is equal to 2, right? So that is the most typical one, okay? Most typical set, okay? The set size is largest as well. So if we gather up, typical sequences plus epsilon and minus epsilons much, so you can gather them up to 95%. Then it is the size of the typical set reach up to a million. Okay, so that's the result of exact calculation, and you can compare that with the typical set size, which is 18,000 right here, and probability based on typical set argument is this. Okay, so you can compare these two calculations. All right, so that's that. So from the argument, from the examples I have given you so far, we can, think about the consequences of AEP. So basically, we can do some data compression. So the size of the typical set is 2 to the power of NH, take away or add epsilon much. Then basically, in order to describe this many elements in the typical set, you only need n times h, nh bits, right? So that's the number of bits you would need, okay? But in the case that this number is not integer, so you add 1 bit to make it integer. So you have nh plus epsilon plus 1 bit to represent each sequence within a typical set, okay? And with a very small probability, you have a sequence belong to non-typical set occur, right? What do you do when such thing happens? Then you have to, allocate. You have to, represent it as well. So in order to do that, how many bits do you need? Basically, you need this many bits. Basically, it is the size of the symbol alphabet and then taken to the power of nth power, okay? Power of n. So in this case, you don't get any data compression at all, any data compression effect at all. And then also you need to add 1 bit in order to, distinguish between typical set element versus non-typical set element. So when you use to represent an element belongs to non-typical set, you have to use certain prefix, let's say prefix 1. So if you start with 1, then you mean non-typical set element. Then you have to allocate this many bits to represent each element, okay? But so this one will be very, very long, I mean, you need you need many bits, right? Because this one is very large, right? And size of the alphabet taken to the power of n, right? So this is very large. Okay, so if n is 100 and this is binary, then you need 100 plus 1 bit, right, for prefix. So you don't get compression at all, any compression at all. But in this case, you get lots of compression, okay, because this one is much smaller than this one, okay. So overall, you will get large amount of compression whenever you have entropy smaller than 1 in the case of a binary, right? Whenever you have entropy smaller than the case of uniform distribution. Okay, uniform distribution, you have maximum entropy, right? So that is the case that each symbol occurs with equally likely case, right? But this typical set is small, but the probability wise, it is close to 1. That whenever you have an experiment, there is an outcome, and that outcome belongs to the typical set. So with the probability very close to 1, you will have this case. You will have a case you will have a sequence. You can represent it with this many bits, okay? And then with a very, very rare chance, you will have to allocate this many bits to represent the sequence. That happens whenever you have an element from non-typical set occur, okay? So overall, because these sequences rarely occur, so the expected value of the number of bits that you would need to represent any sequence in the whole set is this, okay?